Consider a beam as shown here. When the beam is loaded, internal forces such as shear forces, compressive and tensile forces develop within the beam. In a case of pure bending, there will be only compressive and tensile forces. The fibers on the loaded side are under compression and the fibers on the other side are under tension. Due to this reason, the fibers in the loaded side shrinks in size and the fibers on the other side get elongated. The compressive force of compression and the tensile force of tension develop a moment about the neutral axis or neutral plane called the bending moment. Between these two kind of layers of fibers, there exists a layer whose length is exactly same as before bending, called the neutral surface or neutral axis in two dimensions. Let AB be the neutral axis and CD be the layer of the beam at a distance y from the neutral axis. After being bent by a load, the length of AB remains same while the length of CD is increased. This curved beam forms a perfect curvature of a circle with radius r and center O. Let the angle made with the beam be theta. The strain on CD is given by change in length divided by the original length, that is r plus y theta minus r theta divided by r theta, which reduces to y by r. Let E be the Young's modulus of the material of the beam, then the bending stress is given by sigma is equal to Young's modulus E multiplied by strain, which is sigma is equal to Ey by r. The bending moment is equal to the integral of stress, which is the force per unit area, multiplied by the distance y. Here, dA multiplied by stress gives us the force acting on area dA and not on unit area. On taking E by r out of the integral as constants, we get integral of y square dA, which is the area moment of inertia of the beam, which is denoted by I here. For a rectangular beam, the area moment of inertia is equal to BD cube by 12. And for a circular beam, the area moment of inertia is pi r power 4 by 4. We can combine this equation with the bending stress equation, which we have derived earlier, then we get flexure formula. This equation tells that bending stress increases linearly as the bending moment from the neutral axis increases and decreases as the area moment of inertia. Our next goal is to find the expression for depression of a cantilever. Consider the cantilever shown here. One end of the cantilever is fixed at point A and the other end is free initially. Let that point be B. When the free end is loaded by a load W, the cantilever bends and reaches B dash. Let L be the length of the cantilever. Consider an element PQ on the cantilever before bending. After bending, it reaches P dash Q dash. Let R be the radius of curvature of P dash Q dash. The bending moment of the beam is given by YIG divided by R, where Y is the Young's modulus of the material of the beam, Ig is the geometric moment of inertia or area moment of inertia of the cantilever. The deflecting couple due to the load W acting at P''Q' is given by W multiplied by the perpendicular distance L minus X, which is shown in the figure. During equilibrium, the bending moment equals the deflecting couple. In this equation, the term 1 by r is the rate of change of the slope. Then we can write it as shown here. Substituting the second derivative of the depression y for 1 by r, we arrive at this equation. Now we integrate this equation with respect to x, then we get the expression for dy by dx as shown here.